Our next speaker is Chandra Chekuri from University of Illinois, Urbana-Champaign, and he will talk about submodular function maximization with packing constraints via MWU. Thank you very much.
I usually don't tell jokes, but I thought I'll tell one because it's kind of based on truth, right? So I was trying to decide whether I should come or not because the schedule was very tight. And I had to convince my wife, actually. This happens to be our wedding anniversary also today, right? And so I was telling her that, Israel is the Mecca of TCS. I really said that. Then I had to stop myself, right? So that won't go well. Maybe they won't let me in, right, if I say that in the entry, right? So to atone for that, I went to Jerusalem yesterday and went to the Western Wall. So hope I'm kosher now, okay? All right. Okay, so this is about submodular function maximization, well, this is not working. Let's see. Okay, I may have to use this. So let me start with a very simple problem that we all know, which is related to set cover, that I'm giving in a set system, so a collection of sets over some ground set, and here x1, x2, xn, n here is referring to the number of sets, and m is the number of elements, and the goal is to pick k of these sets to maximize the union, okay? And it's a dual version of set cover, very simple problem, well studied, and here is an example of k equal to 3. I chose these 3 sets, and it's also the same as k equal to 2, and maybe that's the optimum solution for k equal to 2. And everybody probably knows about the simple greedy algorithm, which gives a nice approximation for this problem. What is the simple greedy algorithm? You pick the largest set, remove the covered elements, pick the next largest set in the remaining solution, and keep going. It's a very simple algorithm. And long ago, right, in a very general context, Nemhauser, Wolsey, and Fisher showed that you'll get 1 minus 1 over E approximation for this simple problem. And not only that, we know that this approximation is tight due to a result of Uri-Feiger. It's a very classical result. So my goal here is to extend or build on this idea of a greedy algorithm for this simple problem to more general problems involving submodular functions. And just to make sure, Mekar already told us about submodular functions, just to be on the formal side. Here we are talking about a set function over a ground set of size n. So f is a real valued set function, and it is called submodular if it satisfies this diminishing marginal utility property that if you take 2 sets A and B and look at an element j which is outside B, what is the value of j to A? It is f of A union j minus f of A. So I'll use plus as a shorthand notation to avoid the union. Then the value to A should be bigger than the value to B. That's a standard notion of submodularity. And one can simplify this condition, and this is kind of useful when we talk about some continuous extension, that you can restrict B to be just one more element than A. For every element, every set A, and where B is A plus I, you apply that inequality, it's the same as that. There's an equivalent characterization, which is maybe more common in some other settings, which is written that way. But we'll work with this first definition. So it's well known, and let me give a couple of examples. The coverage function is submodular, and so it's a little bit confusing with a lot of sets being thrown around, right? So when you think of the coverage function, how do we think of it as a submodular function? We ignore the elements. We only think of the sets. Right? Each set becomes an element in the ground set, and what is the value of taking a few sets? It is how many elements they cover. Right? So the sets are a little bit confusing, but this is a well-known notion. And so max K coverage is, in some sense, coverage functions are submodular. And another canonical example of submodular functions is the cut functions on graphs. Right? If you give me a graph and look at the vertices as the ground set, and what is the value of a subset of vertices? It is how many edges cross that set. That's also submodular. It's not a monotone function. So it's useful to think about submodular set functions in this context in terms of some canonical ways. One is the monotone submodular functions. Monotone submodular functions have the property that the more elements you take, the value increases. right? F of A is less than or equal to f of B for all A subset of B. Non-negative is less restrictive class. It doesn't have to be monotone, but all the values are non-negative. And symmetric is when f of A is equal to f of n minus A. And the coverage function is monotone. The cut functions in directed graphs are non-negative, but not necessarily monotone, while cut functions in undirected graphs are symmetric, which are not monotone. So these are some canonical examples. There are many, many examples. Okay. So a broad class of problems of interest to us is this constrained submodular function maximization, right? So what is this class? Here we want to maximize f of s subject to some conditions on S, right? So the simplest one, which is the motivating example, is I want to maximize f of s subject to picking at most k elements from the set, right? K elements, right? And if f is a coverage function, that is a maximum k cover problem, right? So that's very simple. And then people have studied many extensions of that, right? So why is that? You know, that constraint is where the most basic one. You can say I want to find S is an independent set in a matroid. That's a very simple matroid. So why not all matroids? Because we know how to solve the maximum weight independent set in a matroid efficiently. So that's a natural class. And why not one matroid? Let's do more than one matroid. And in this talk, I'll be interested in packing constraints, and I'll define them formally later. But in general, we can ask this question, right? You know, I want to maximize submodular function. The objective is submodular. I have some constraint. Okay, and this is a very classical topic. It was studied in the late 70s by Nemhauser et al., right? And I think forgotten in our community for many years, and rediscovered. Right? You know, it keeps getting rediscovered. And you know, just to, right, you know, there's a lot of progress in the last 15 years, I would say, and there's still lots of papers, especially in machine learning conferences, our conferences, and so on, right? So my goal in this talk is not to give a survey, right, but to kind of that was intentional, right? You know, if anyone noticed it on the slide, but so we have to do it these days that way, right? Otherwise, okay. So I will not be able to mention many papers, right? That's not my goal, right? What I want to do is I'll say what I want to do, but let me just say that I'm going to in this talk focus on this particular issue, right? This particular class of problems, right? What is that? I want to maximize the submodular function subject to some packing constraints, right? So what are these packing constraints? That are explicitly given in the form of a matrix A and a vector B, and I want to satisfy the property that the set I pick has A times 1s is less than or equal to B. Okay? So this is a kind of a weird notation, right? You know, what it is saying that, you know, my constraints are of the form Ax less than or equal to B. X is an integer vector, binary vector. Right? That's the same as this, right? So I have many constraints, right? Instead of one cardinality constraint, I have many constraints with arbitrary coefficients. Okay, is the problem clear? Yeah. Okay, so this is a. So why is this interesting? It's interesting because it captures many natural problems that we want to study, right? Like, you know, you can take partition matroid and lambda matroid constraints, knapsack constraints, matchings, resource allocation problems. So it's a very, very general model. Okay, so at the same time, it has some tractability properties. So I would like to explore this a little bit in this talk. Okay, okay. So in particular, if you think about f being just a modular function, right? Suppose you want to solve maximum weight matching, right? That's a special case of this, right? And you want to solve many other problems. Even when the function is modular, the only way to solve this general class of problems is via essentially linear programming relaxations. Okay, so it's not very easy to do combinatorial approaches directly because the class of constraints is pretty rich. It involves numbers and not just combinatorial constraints like matchings and so on. So, okay, so traditional approaches based on greedy algorithms and local search are not quite directly suitable for this rich class of problems. And so for this, you know, the mathematical programming approach for submodular function maximization turned out to be the necessary tool to attack this problem. And in fact, we started this in a long time ago. It's long by now, right? You know, it seems like a lot of time has passed. And the initial goal was not really to attack this problem, but to solve something else on matroids to improve the ratio. But it turned out to be very useful for packing constraints as well. Okay, so what is this mathematical programming approach, right? Many of you know this, but so in this approach, we want to solve this discrete optimization problem. We want to relax it to a continuous optimization problem in some way, where we let the variables become fractional, right? So the natural way to relax it is to have ax less than or equal to b, where x is fractional between 0 and 1. But the question is, what do we do with this objective function which is submodular? If it is a linear function, this becomes easy. It becomes w times x, while it's a submodular function, so what do we do with it? And then we also have to worry about rounding, right? What do we do if we solve this? How do we round this, right? So there are many results by now based on this approach, right? So it's a kind of well-solved problem by now. So it's not, I'm not trying to say anything new on that front. What I would like to explain is that the limitation of this approach so far has been that it's pretty slow. And I want to see how whether we can get the benefit of using the mathematical programming approach while making the algorithms fast. Okay? And that's the main focus of this talk, right? How do we make this approach fast because it's kind of slow, right? So before I get there, I need to tell you, I didn't tell you what this relaxation is. You know, how do we take a discrete function and make it into a continuous function here? It's not quite obvious what to do. And in this work, we were inspired by some previous work of Agiv and Sviridenko and defined what is called the multilinear extension of a submodular function. It's very simple. So given a discrete set function f, right, we can define a continuous function, right, in the following way, right? You can use it for any function. So how do we do that? So we want to take, so we need to assign some number for every fractional point in the hypercube now, right? And we do it by the following way. We take R to be a random set where each element is picked independently with probability xi. And we take the expectation according to the original set function f. Okay? That's one way of assigning a number to each fractional point in the hypercube, right? And in algebraically, it is just a very simple formula, right? You look at all subsets of n and look at what is the probability that set will arise. It is precisely this, right? And then we take the expectation. This is the expectation is the same as this formula. So it's called multilinear because this formula is linear in every variable xi. Yeah, it's okay. So it has some very nice properties, right? And I'll go through some of these properties that if f is submodular, capital F inherits some very nice submodularity properties. So let's go over them a little bit. F turns out to be neither concave nor convex. But one nice thing, and the reason it's nice is that you can estimate both the function and its gradient by random sampling, just from the formula, right? From the definition, you can estimate it by random sampling, right? You repeat it, take averages, right? So what are some nice properties that it satisfies, right? It satisfies the property that the partial derivatives are less than or equal to 0. Second partial derivatives is less than or equal to 0. For every xi and xj, the second partial derivative is less than or equal to 0. And why? What is the intuition for this, right? And if you look at you can do it by formula, but really all it is saying is that submodularity property that I defined earlier, f of a plus j minus f of a is bigger than f of a plus I plus j minus f of a plus I. This is equivalent to this in some sense, right? So this implies this, and so it is this. And secondly, the diagonals in the Hessian are all 0 because of multilinearity, right? Because it's linear in each variable, the second partial derivative in the same variable is 0. In particular, these properties imply that f is concave along any non-negative direction, and I'll put a picture because that's more intuitive. And moreover, if f is a monotone function, all the gradients are always positive, and if x is smaller than y, coordinate-wise, and the function value is larger. Okay. Okay. So this is the key property of this multilinear extension. So if you take x and you look at the point x plus d, where d is bigger than or equal to 0, and look at the function value along this line, it's a concave function. Okay. So in particular, it means that if you look at the gradient at this point times the inner product of the gradient and this d, it has to be bigger than f of x plus d minus f of x, the concavity. Okay. This is the key property. Yeah. Okay. Very simple. Nice. It inherits nice properties from the underlying submodularity function, right? Okay. So now let's get back to this problem, right? What we would like to do is we want to solve this discrete optimization problem. Instead, we try to solve this continuous optimization problem and then try to round it. Okay. Now the question is, how do we solve this? Because this is neither concave nor convex, so you cannot use standard continuous optimization techniques. Moreover, from existing results, it also follows that solving this is already NP hard even for the cardinality constraint, exactly, because it's equivalent to solving the discrete optimization problem. Okay, that comes from some rounding reason. So the very beautiful result of Jan Wondrak is that, in fact, you can approximate solve this within 1 minus 1 over e for any polytope which is reasonable, where you can do linear optimization. Okay. And this is the famous continuous greedy algorithm. It builds on the discrete greedy algorithm, and it's very nice. So in some sense, we know what to do, right? To solve this, we use this result to get an approximation here, and then we round. There are many nice rounding techniques. We know a lot, right? So as I said, the only limitation is that, and then there are lots of work on extending to non-monotone functions, improving it. Moran has done a lot of work in this area. So there's a lot of things to say here. But what I'm going to focus here is, can we make this algorithm fast? Okay, because this algorithm is pretty slow. Conservatively, it will take a lot of calls to the underlying function f. Okay. So how do we make this algorithm fast? Well, we don't want to live in this full generality of any solvable polytope, because if we do that, then we are not going to really understand what the polytope is. So my goal in this talk is to tell you a little bit about how, if you restrict your attention to this large and interesting class of packing constraints, how you can solve this pretty fast, both sequentially, and in fact, I want to give a little bit of flavor of how we can do it in parallel, because that's been a lot of papers in the last year, actually, right? And in fact, the sequential thing is also not very new. It's a paper from 3 years ago. In fact, at ITCS, it was in Israel. I couldn't come, so Jairam came for this. Maybe this is an opportunity to give that talk, right? But I want to also focus on a more recent result on parallel algorithm, again based on some continuous optimization technique, right? And it's very simple, so I want to highlight some of this, yeah. And I'm going to ignore the rounding part. I just want to tell you, I want to solve this relaxation fast. How do I do that? Okay. And what is the measure of performance? The measure of performance will be how many oracle calls to the function I make, or how many oracle calls to the gradient I make. Okay. And I'm not going to be very precise about these results, because I'm trying to convey maybe some simple key ideas on how to use the continuous relaxation in a simple way. Yeah. So I will see, and in the parallel world, we'll talk about the depth. Okay. So that's sort of like the basic introduction, which is kind of fast. But so let's try to solve this very simple special case. Okay. I want to maximize this multilinear relaxation subject to one knapsack constraint. Okay. Just one constraint. Yeah. And then we'll see that this is all there is to it. Right? Once you understand this properly, then we can extend it to many things. Okay. And how do we solve this? Well, in fact, Wolsey solved this in '82. It's not a very well-known paper, right? And of course, Jan also solved this because it's a special case of his result, right? Okay. But I'm going to go to Wolsey's result because it's actually simpler and easier to understand. Okay. And so what is this algorithm? The algorithm says, it's very much like the discrete greedy algorithm, right? You simply look at each time. It's like a continuous algorithm. We'll do it in a continuous time, and then we'll kind of discretize it. You say, what is the coordinate which has the best gradient divided by A? Okay. If you want to do a greedy algorithm, what would you do for this problem? You would look at the element which has the largest marginal value divided by the size it contributes to the knapsack constraint. Right? So I'm doing the same thing except in continuous time. Right? What is it? I'm looking at the gradient, which is the proxy for the partial derivative, sorry, the gradient with respect to that coordinate divided by the size of that item. Right? And I add a small amount of that item to my current solution X. Okay? Yeah? Okay. And finally, our output X, right? I will tell you, what is the small amount, right? But initially, I'll just assume it is continuous. It's a very tiny step.
You compute the derivative by numerical approximation?
Yeah, numerical approximation. Sample. Okay? Because f is defined as sampling, I can do by estimation. Okay? Yeah, I can't do it exactly, but that's fine. Yeah? Yeah, there's some issues here, but let's assume we can solve it. Yeah? Okay. Okay. So how well does this do? I want to claim that, remember, I'm not trying to solve the discrete optimization problem. Right? I'm trying to solve the continuous optimization problem. I want to claim that I'll get a 1 minus 1 over E approximation via this algorithm. Okay.
But why do you have to make a small step? You are guaranteed, due to the kind of single peak property, you can estimate how far you can go before you lose out to others. Can't you?
Yeah, you could do that. No, I'm just going to, but in fact, I can do much more. I'll come to that. Yeah, right. There is a lot more going on. Yeah, right. But just to analyze it from the first, I'm going to analyze two parts: the approximation and how fast this algorithm is. Right? Yeah. Okay. Yeah, and that's a good point. We'll come back to that. Okay. First, I want to claim that if you do it slowly enough, you will get a 1 minus 1 over E approximation. Okay. Okay. And okay, now let's do that, right? So what is the key thing? That is submodularity, basically. So your X is your current point. Let X star be, and oh, by the way, I'm only going to work on monotone functions for this talk. Okay. I'm not going to worry about non-monotone functions. Okay. I forgot to say that. Okay. So you're at X. This is the X star is the optimum point. Okay. I don't know that. But let's look at this direction from X to X or X star, which is a coordinate-wise minimum. Okay. What is X or X star? It's a coordinate-wise minimum of X and X star. So this direction is always positive. Yeah. Okay. Remember that the function is concave here, right? That's a benign property. What does that imply? That if I look at the gradient of the function at this point and look at the inner product with this direction, then that's at least as big as the value of f here minus the value of f here. Yeah? Okay, but the value of f here is at least opt because of monotonicity. Yeah? It's at least f of x star, so this is at least, right? So my gradient, the inner product of the gradient with this direction is at least opt minus f of x. Okay, this should remind you of the discrete greedy analysis if you have seen this before, right? Okay, so okay, there's a lot of algebra here, but the point is that monotonicity guarantees that all the gradients are positive, all partial derivatives are positive. So if you just take this equation, this inequality, and expand it out and use this property, you can argue that the sum over all coordinates, the gradient with respect to that coordinate times x star j is bigger than opt minus f of x. Okay. And we also have this inequality that, because of monotonicity, the sum of aj x j star is equal to b. Don't worry about all that. What you can argue is that the ratio of the maximum gradient over AH is bigger than opt minus f of x over b. Okay. This should remind you very much of the discrete greedy algorithm, right? The bang for buck I get is at least what is the residual value divided by the knapsack capacity. Okay. You're getting this in the continuous world. Okay. So once you have this inequality, you will get 1 minus 1 over E. That's a standard analysis. I won't go through it because it takes time. If you've seen it, it's easy. If you've not seen it, it looks a little mysterious, but nothing really interesting going on. Okay? So once you have this, you know that you get f of x, if you follow this differential equation, you'll get 1 minus 1 over b to the b, which is 1 over r. Okay, what have we gained by this? I haven't really gained anything, it looks like, right? Okay, so I want to claim two things, right? One, this is not the same continuous greedy algorithm of Yann, by the way. For those who are familiar with Yann's continuous greedy algorithm, this is not Yann's continuous greedy algorithm. It's very different. But it's very simple because you have a single knapsack constraint, right? What have we gained by this? Have we gained anything, right, by this algorithm? And first of all, how do I make that step? How do I make that steps, right? Here is where a very nice thing happens. I claim that this algorithm is the same as the following algorithm. Okay, what is this following algorithm? At each step, you compute this the coordinate with the maximum gradient over AH and take it fully. The step size can be fully. Why is that? Okay, that is because f is multilinear. Okay, what does it mean? That once the gradient of a guy is good, let's look at the top guy, right? As I change him, his gradient doesn't change. Okay, so let's say the first guy I pick is the highest gradient. As I change him, his gradient remains the same because it's multilinear, right? And the rest of the guy's gradient can only get worse because I'm increasing one guy. So there's nothing stopping me from taking this guy all the way, right? So I will take him all the way till I can't take him anymore because he reaches 1. So that's okay. So I claim that this continuous algorithm can be completely simplified, and this is the same as find the guy with the largest gradient, take him fully, then recompute and find the next guy with the highest gradient, take him fully, until you run out of knapsack capacity. Okay? So this is a very simple algorithm with a nice property that the number of gradient calls is much less than what you would get if you just applied Yann's continuous greedy algorithm. Okay? And it's actually essentially is there in Wolsey's old paper. Okay? Any questions on that? Nothing mysterious going on here. Okay? What I want to say is that the number of gradient calls has become much less. It's O of n, it's not small, but still it's much less than what if you didn't use a single packing constraint. Okay? Okay. So what I want to do next is to show that you can get a very simple parallel algorithm by sitting in the continuous world. Okay? So I want to say the same problem, but now I want to solve this in parallel. Okay? Okay. So far, I mean, it hasn't been considered very much in the literature so far, these parallel algorithms, till some surprisingly, very recent work of Balkansky and Singer from Stock 2018. For reasons that are not necessarily due to parallel computation, they were interested in a parallel algorithm. Okay. I think their motivation was different, but let's just say they want to solve this in parallel. Right? So parallel algorithms for set cover and maximum coverage are classical. Right? And a lot of people have them. There are several stock papers on parallel algorithms for set cover and maximum coverage. So this is a much more general version of that. Right? You want to maximize an arbitrary submodular function given as a value oracle subject to the cardinality constraint, right? So can we parallelize it, right? And so so what does this mean to parallelize this algorithm, right? So you have to be a little careful about the oracle model, right? Okay, you cannot parallelize the algorithm if you cannot evaluate the algorithm in parallel, right? So let's assume for simplicity that somebody gives me an oracle to parallelize f, right? If you can't do that, then why are you solving an optimization problem, right? So let's assume for simplicity that we can evaluate f in constant time in parallel, or you can evaluate f. Assuming that you can evaluate f efficiently, I want to maximize this. Okay? And there are lots of papers in this last year, and they showed that how you can parallelize, solve this in parallel. You get 1 minus 1 over e approximation in this much depth. Okay? And they're all kind of complicated. I want to show a very simple algorithm, right, which it comes from the continuous viewpoint, okay, and how that extends to other settings. Okay, so I'm going to build on the previous the few slides I've done to show how to get a parallel algorithm for the same problem using continuous optimization. Okay? Okay. So instead of solving that, I'm going to try to solve this now. Okay? So remember, I want to maybe solve this problem, but I'm going to try to solve this problem instead. And we know that if you can solve this, you can get the same approximation because this is a simple cardinality constraint. There's no loss in going from here to here. Let's ignore that issue. Can we solve this fast in parallel? Okay? The only thing we gain here is that this is a very, it's a continuous optimization problem, so it has some nice advantages, right? Okay. So how do we solve this in parallel? Okay. We take the sequential algorithm and we try to push it to its limit, right? By trying to do the following, right? What is the natural idea? What did the sequential algorithm do? At each step, it looked at a coordinate with the highest gradient and tried to increase it, right? Okay. I have to do it in parallel. I can't just wait around, right? So what am I going to do? I look at all the things which have a good gradient and I'll say, let me increase all of them. Okay? Well, that could be bad, right? I mean, if I increase everything in parallel, maybe I shouldn't increase all of them in parallel, right? But I'll be very greedy and actually do it, right? Okay, so here is the algorithm. Remember, I mean, I simplified it a little bit. Now all the coefficients are same. So that actually makes a notation a little easier, right? A's are 1. Okay, now the ratio is a little better. So what is the algorithm? You say, okay, let's look at the maximum gradient, right? Current best gradient, right? Now I compute all the coordinates which have comparable gradient to that best gradient. Okay, what is S? S is set of all coordinates whose gradient values are at least 1 minus epsilon times the best possible gradient. Yeah?
But it could be a single one.
It could be a single one, right? But this is the set of all good coordinates. I say, okay, let's increase all of them. Yeah? Because they're good, and why not, right? Okay, so how much? I have to be careful, right? If I increase all of them simultaneously, maybe they'll clash with each other, and I can't increase it, right? So how big of a step should I take? I'll be greedy, and I say, take your idea, right? Take the maximum I can do so that I don't get any harm in the value. Okay, what does it mean? So I have to be a little careful. I choose the delta as big as possible, yeah, such that I don't harm myself. Okay, how do I quantify I don't harm myself? If I look at the delta after taking that step, what should I get? I should get at least 1 minus 2 epsilon times lambda times delta times S. This is the simple quantification of what it means that I can go as far as I can without losing too much. Okay? Remember, if I increase only one guy, I should get lambda times delta, right? That is the gradient, and I take a small step, I should get lambda times delta. But I'm increasing S guys, so I should get lambda times delta times the size of S. I'm giving myself some slack here. That makes sense? This is
if S includes more than one coordinate,
yeah.
So you force the same step size in each direction?
Yeah. All of them go by a small amount, exactly. Yeah.
Get more if you allow more flexibility?
Yeah, but I'm not, right? I want to do this in parallel, right? If there are many good guys, I want to increase all of them, right? But I don't have time to, I mean, in the sense of parallel sense, right? I don't want to look too closely, how much can I increase this guy? I'm just going to increase all of them, as much as possible. Maybe this delta will be very small, right? Imagine I'm solving a maximum coverage instance and all of them are overlapping. They all look good, but I can only take one guy, right? Because if I take all of them, if I take one guy, it'll kill all of the things, right? But fractionally, I'm saying, take all of them a little bit. If they're all good, let's take all of them a little bit till I get into a danger zone. Maybe the delta will be very small, right? It will be 1 over n step, right? So is this any good, right? Doesn't look like a very good algorithm, right? It turns out it's actually a nice algorithm, okay? Why is that? First, I want to say that if you don't care about time, I am doing the right thing as if I'm doing sequentially, right? I'm picking all the guys who are good gradient. I'm going as far as I can so that I don't hurt myself. So if I think of it as a sequential algorithm, my approximation should mirror the sequential approximation, right? Does that make sense? Because I didn't do anything bad, really, right? from an approximation point of view. Yeah? So you would believe me that the approximation will be 1 minus 1 over E, because it is essentially the same as a sequential algorithm. Yeah? Any questions on that? That seems reasonable. Yeah? Okay? I mean, it's not any worse than sequential algorithm. I mean, it's slightly worse, but not much worse. Right? So that's why I lose this effect. The question is it any good from a parallel point of view? Yeah? Okay. Because the step size could be extremely small. Okay, the claim is, because we took this greedy step size and I chose this a little bit carefully, the claim is that after the greedy step size, the size of this set goes down by a 1 minus epsilon factor. Okay, so let me go back to the algorithm, right? What happens? You start with the best gradient. What did you do? You picked all the good coordinates and you increased all of them by a little bit, as much greedily as possible. But I'm not done, right? I go back to this loop. Maybe some guys will drop out in this next iteration, right? If I can keep going with S, I would go as far as possible, right? But when I come back, remember, lambda doesn't change, right? But S goes down maybe, right? Now, not all guys in S will be good, right? And I keep doing this with the same lambda till I am run out of any person who's any coordinate which has a good gradient with respect to that lambda. And then I go back up, I would say, okay? So my claim is that after this greedy step size, the size of this must go down at least by 1 minus epsilon factor. Suppose you believe that claim, okay? Let's look at how many times will you repeat this inner loop for a single value of lambda. Well, each time I do this, the size of S could start with n, right? All of them could be good. Once I do this, they will go down by, the S will go down by 1 minus epsilon. And I do it again, right? So the number of times I repeat this iteration is how many times? It's just log n over epsilon times. Because each time the size of S is going down by a small constant factor, right? Okay? So that's the inner loop is only log n over epsilon. What about the outer loop? Well, lambda goes down by at least 1 minus epsilon. Because, at the end of this, the lambda has to go down by 1 minus epsilon because I gave myself some slack. Okay? Right? Okay. The claim is that if you believe, right, that S goes down by 1 minus epsilon factor in one iteration, then you should believe this algorithm is good. Yeah? Why? Because inside iteration is log n over epsilon. Outside is also roughly log n over epsilon because lambda goes down by 1 minus epsilon. You have to do some tricks, but yeah. Okay, so that's it. That's the algorithm. Okay, so I hope it is very simple, right? You looked at all the good guys with gradient, made sure that you took all of them in simultaneously, and yeah. Okay, so why does the S go down by 1 minus epsilon? Okay. So that is a consequence of the greedy step, right? Okay, let's do a little bit of proof, not too much. And you can improve that log square n to log n, let's not worry about that. Okay, so let's argue why after the greedy step, S goes down by 1 minus epsilon factor. Remember, S is a set of all good coordinates at the lambda, and S prime is a set of all good coordinates after you took the greedy step, okay? And I want to claim that S prime, size of S prime is less than 1 minus epsilon times S, right? Because if this, my claim is S goes down, right? And this is before the step and this is after the step, right? And where Y is X plus delta S. Make sense? Remember, we started out with S being the set of all good coordinates and we took a step size, the largest step size that we can of X plus delta S. At the end of it, S prime is a set of coordinates which are still good, right? And I want to claim S prime is small. Suppose S prime is not small.
It should be S prime less than 1.
No, I'm getting a contradiction by assuming S prime is bigger than, right? Suppose S prime is big, right? Even after this greedy step size, then my claim is that this delta was not optimal. I could have gone a little further. Okay? Okay, that's the idea, right? If I didn't go down, it means that I could have kept going, right? Why? Because of the slack of 1 minus 2 epsilon here and submodularity. Okay, it's hard to see the math here, but it's saying, if there was a lot of good coordinates which were still very good after the step, it means I could have gone a little further.
The algorithm and the proof are still in the case of a single constraint? Or
A single constraint.
Because if you have multiple constraints, you hit
No, single constraint. I'm in a very simple world, right? Okay? So I won't do the formal proof, but that's the idea, right? And that's it. That's all the algorithm, right? Okay? Very nice, right? I think it's very simple, right? You don't have to, there's nothing mysterious about it. Right?
And do you have any lower bound on the number of runs that you need?
So for the discrete problem, yes, there is a lower bound of log n over log n, which is shown by Balkansky and Singer. Yeah, you can't get better than log n over log n if you want a constant factor. And because we are solving the continuous thing and it's equivalent to the discrete thing, it applies. Yeah. Okay. One nice thing is that this algorithm is deterministic if you have access to the gradients. Okay. While so it's only implicitly that we use randomization, and you can make it. Yeah. So I won't spend much time on this. That you can do this by binary search, and you can convert the continuous extension. You can round the algorithm, round the solution in the end. Okay. Okay. That's all I want to say. Okay. Now let me go to multiple constraints. In how much time do I have? Oh, that's all. Okay. Okay. So to do the multiple constraints, I claim that there's some standard methodology will work. Okay. So what is the standard methodology? It is the multiplicative weight update method. Okay. So now I want to solve this problem, right? I have many constraints, right? Okay. Instead of one, and moreover, I'll normalize the right-hand side to 1 for simplicity, right? Okay. What is the multiplicative weight update methodology? Right, in a nutshell, right, what does it do? I mean, we adapted it for submodular function maximization in this 2015 paper. What it does is, it takes this problem and reduces it to iteratively solving a single constraint problem. How? It takes weights on these constraints and linearly adds all of them, okay? So you take a relaxation of the original problem by taking a non-negative weight on each constraint and solving the Lagrangian relaxation obtained by multiplying each constraint by the weight and adding them up and getting a single constraint. Okay. There are more details here, but it's not actually very important. Okay. So to solve this problem, you relax it to this single constraint problem, okay, and then you repeatedly solve this single constraint problem, and you repeatedly update the weights in an exponential fashion, and until some termination condition happens. Okay? So, but the key is that at each step you're solving a single knapsack problem, right? For that we know what to do, right? We pick, what should we do if I gave you this problem? We know how to solve this problem, right? Okay? So to solve this problem, we repeatedly solve a single knapsack problem, right? So let's look at what the algorithm will look like. Don't worry about all the details. When you're trying to, so to solve this problem, you're repeatedly trying to solve one constraint problem. What would you do? You would pick the item with the highest gradient at that point. That's the right thing to do, right? We already know that if you had a single packing constraint, you should pick the item with the highest gradient divided by its coefficient. So that's all this is doing. At each step, pick the coordinate with the highest gradient divided by the AH, where these coefficients are coming from these weights. Okay? You take a small step in that direction, you update your weights, and repeat.
So intermediate values might not actually be feasible points.
Yeah, but
you have two constraints which you are mixing together. One might be too big.
Yeah. Yeah, because the weights are increased in exponential fashion, if you do it slowly enough, you will eventually satisfy the constraints. That's really what it is, right? Okay, but I don't have time to explain all this, but the point I want to convey is that once you have this machinery in somewhat a reasonable fashion, you can turn the crank, right? If you turn the crank, the algorithm is fairly simple. You do some tricks. The point is, here, what controls the step size is because you have collapsed all the constraints into a single constraint, you cannot take too much of a step, right? What controls the step size is the increase in the weights, okay? The weights have to be exponential in the load, and you have to do it slowly enough. And what should you do? There's a simple principle which came from Garg and Kahneman. It's called the greedy rule, what you described, is that take as large a step as possible so that you maintain your weight invariant. Okay? Okay? And that's a simple idea, and if you do that, you can argue that the number of iterations of this algorithm is only m log m or epsilon square. M is the number of constraints. Okay? Now, what have we gained by all this, right? I'm running out of time. What you're gaining from all this thing is that using this single knapsack algorithm inside the multiplicative weight update method, you can reduce with some tricks the total number of gradient evaluations you need to n polylog over epsilon square. Remember, for a single constraint, we needed n gradient evaluations, right? Now, even with a lot of constraints, the number of gradient evaluations is still linear in the function. Okay? So, for a very large and powerful class of constraints, the number of gradient evaluations you need is only linear in n, with modulo polylog factors. Right?
Did the dependence on the size of the coefficients in A enter somewhere?
No.
Because I can think about very large coefficients in one linear inequality, very large coefficients in the other one. You start by having W, which is 1 everywhere.
Yeah.
So you mix the two and you get small.
No, the number of iterations doesn't depend. The numbers in the middle will depend, but not the number of iterations. Okay? So it's width independent, it is called. This running time is width independent. It doesn't depend on the numbers. So you have to be careful, but yeah. Okay. So I want to close by saying that now I want to do this in parallel. Okay, right? The same thing, multiple constraints, but I want to do it in parallel. But we have all the ingredients I claim, right? What do? We basically take the two ideas, right? The multiplicative weight update method allows you to collapse everything into a single constraint, but that we know how to solve in parallel, right? We already saw that, okay? So we just combine the two. I mean, it's a little bit too simplistic to say that, but really at the high level, right, as an advisor to my student, that's what I said. Combine the two. And the student comes back and said, yeah, it worked, right? I'm simplifying it, of course, right? But that I want us to, I just really want to convey that that is the mindset, really, right? You know, once you have the two ingredients, you can try this, and it actually works, right? But you have to be a little careful. The parallelizing this multiplicative weight update algorithm, it requires a small tweak, which is maybe not too late in the day in the talk to explain, but you need to be a little careful, but you can combine these two. Okay? So really the algorithm is very simple, right? You know, it is at each step look at the maximum gradient value and simultaneously raise all the guys with that gradient value and you stop because it's not a good step for either the gradient or because you're bumping against something with the weights. Okay? So you have two constraints now. The weight should not change too fast and the gradient should not go down too much. You do the greedy step based on these two constraints and it all works. Okay? And what you can get is a 1 minus 1 over E approximation for the continuous extension. Depth is good, number of oracle calls is good, and everything is theoretically at least fairly good. Okay? So I want to there's a lot of recent work on parallel algorithms. I don't have time to say anything about that. I want to show, what I hope to show is that this continuous approach is very powerful, first in getting good approximations, right? That was the initial goal. And now we have many, not just this work, many other works which have tried to get faster algorithms. And I think we have theoretically faster algorithms now for many interesting problems. I don't know if they're really practical yet, right? You know, and I think that requires some empirical evaluation, which maybe is beyond the scope of me at least, right? You know, and one nice question is, can we extend these continuous approaches to other functions beyond just submodularity? Are there nice classes of functions where these approaches give us good results? That may be an interesting question. Yeah. Thank you.
Can you say anything about non-monotone submodularity?
Yeah. So I stuck to monotone functions only because of the proofs are simpler. Essentially, all these things work for non-monotone also. The running times are a little worse. So, for example, in the same paper, we also did the non-monotone case you will get little worse running times here. Instead of n, you get n square. But it works for non-monotone. Also, the parallel algorithms, I mean, not, after we did only the parallel algorithm for only monotone, but there is a new paper of my student, ex-student Alina and co-authors, which got non-monotone. Yeah, many of these algorithms work for non-monotone. Yeah, I wanted to stick to monotone for simplicity. Yeah. Yeah.
When you parallelized, you lost a little bit because you said that you have to be extra careful in choosing how far you go. So how much do you actually gain from the parallelization?
Oh, I mean, the depth is only this much, right? The depth is polylogarithmic. It's sequential algorithm, depth is n, we are getting polylog depth here. This is an NC algorithm.
So if I'm summing up the work of all the parallel processors, how much bigger is it than the work of the single one?
Not much bigger by polylog factors.